So let us now start the exercises. So whatever equations we are going to see here, we have to first of all determine if it's exact or not, and if it is exact, then we have to solve it. And this is the first one, that means the second one actually. So the equation is y squared plus 3 times dx plus 2xy minus 4 times dy equal to 0. So let's see if it is exact first, and if it is exact, then we are going to solve it. So this is how you can write the solution, and you can use this language. The given equation is this: m dx plus n dy equal to 0, where m is y square plus 3 and n is 2xy minus 4. Or instead of this line, you can also write like this: comparing the given equation with this equation, we get m equal to this and n equal to this. That also you can do. And then of course we go for the test for exactness. So we calculate the partial derivative of m with respect to y, because you have only y here, so it will be 2y. And then we also partially differentiate n with respect to x, so that gives us again 2y. And this happens for all x comma y belonging to R2. Oh, and note one more thing, I haven't really written m of x comma y within brackets. Actually that's how you should write, but because of lack of space, I have simply written m and n with the understanding that both of them are functions of x and y. So now we have the condition for exactness true here at all points in the plane, and that is why the given equation is exact in any rectangular domain D in R2. So from our theorem that we proved earlier, there exists the function f from D into R, which of course has continuous first partial derivative. Those things are there in the background, but such that the differential of f is equal to m dx plus n dy, or in other words, del f del x is m, which in our case is y square plus 3, and del f del y is n, which is 2xy minus 4. And these equations also are true in D, that means for all x comma y belonging to D, which however we do not write explicitly. And now you know what to do. We are first of all going to integrate this, and then we will proceed from there. So we do just that, integrating both sides of equation 1 with respect to x, you will get this. On this side you will have f, of course, and on the right hand side, originally we did not have any x. So all the quantities that you see here, 3 of course is constant, but y square is also considered constant. It's not changing as x is changing, and that's why the integral will be y square x plus 3x plus phi of y, where phi of y is an arbitrary function of y only. It does not involve x. And next we are going to differentiate both sides of this equation partially with respect to y, so that we can use this, and that we will do from 2. So from equation 2 we have this. I have kept the 2 equations because we need them now, so I haven't erased them. How do you get this? This you, of course, del f del y equals 2xy minus 4, that's what we are getting from 2. But from here also we are going to get del f del y. So if you differentiate partially with respect to y, x is considered constant, so this term will give you 2yx, and this term will give you 0 because there is no y. And this is a function of y only, so this will be the ordinary derivative of that function, because differentiation is happening with respect to y. So then you notice that you can cancel 2xy, 2yx, same thing from both sides, and that way you are going to get this. Phi prime of y is equal to minus 4. And now you can integrate both sides, of course with respect to y, because x is not there in the picture anymore. And that way you will get phi of y equal to minus 4y. You have to write a plus c constant. However, as we discussed before, there is actually no need to do that here, because eventually whatever constant you are going to get here, I mean if you write a constant, arbitrary constant, that will get merged with the arbitrary constant in the actual solution to the original differential equation. So now we use this value of phi of y back here, and that way we now have f completely determined. So f now equals y square x plus 3x minus 4y. So now using this f, we are going to write the general solution. So the general solution is the first f equal to c, where c is an arbitrary constant, or y square x plus 3x minus 4y equal to that constant. Now let us recall something which we might have already forgotten before we leave this solution. The aim here is to not actually see that whatever we are finally getting is really a solution, that it's either an explicit solution or an implicit solution of the given differential equation. Simply finding a relation like this is not enough. You have to then check if it really is a solution. Right now it's a potential solution. But because the aim here are the methods, we want to know what types of differential equations have exact methods for finding their solutions. We want to learn those methods. First, we want to recognize the differential equation type, and if it is of that type, then we want to know what to do to find a potential solution. So the story actually doesn't end here. If you really want to solve the differential equation, you would then have to show that yes, this is a solution, or this relation contains within it explicit solutions, at least one. But that's a different matter. That won't be done here. We went through the method, and that's what we wanted to do here. Let us see the next one. So the next one is number 4, and the equation is 3x square y plus 2 times dx minus of x cube plus y times dy equal to 0. So let's see if it is exact or not. So for this one, I am not going to write any sentences, anything. Instead, I straight away just take this m, which is 3x square y plus 2, and this n, which is minus x cube plus y. And let me give you a warning here. Do not write x cube plus y. Okay, it's very easy to ignore this minus. Remember that the original equation is in the form m dx plus n dy. So you have to include this minus here, because this minus plays a role in making this equation non-exact. It is not exact. So let's see how. If we calculate del m del y, then x is considered constant. So we get 3x square. This of course will give us 0. And if we calculate del n del x, then y is constant. So we get minus 3x square. These two are not always equal. But of course, there is the possibility for equality for some values of x. So let's see exactly where, for which values of x these two are equal. So our partial derivatives are equal if and only if 3x squared equals minus 3x squared. If and only if 6x squared equals 0, if and only if x is equal to 0. That means the points x comma y at which these two partial derivatives are equal are all the points on the y-axis in our two-dimensional plane. And that is why our differential equation is not exact in any rectangular domain, because no matter how thin a rectangular domain you may think of, it cannot be entirely contained within a line. And by rectangular domain, we of course mean interiors of rectangles, because this is a two-dimensional line. No such rectangle with a non-empty interior can be entirely contained, well, not exactly the rectangle, but its interior can be entirely contained within a line which has no area, it only has length. And that is why this is not exact in the type of region that we want, so that we can apply our method for solving this. So we cannot do anything here. It may have solutions, but we cannot apply our known method here because it is not exact. So next we have 6. Theta square plus 1 times cos r dr plus 2 theta sin r d theta equals 0. Suddenly it confuses you a little. because x and y are not there. Instead you have r and theta. But actually that's not a problem because these are just some variable names, that's all. Because of the way the equation is written, we are going to treat r as our x and theta as our y. Do not write these things, okay? Don't write let r be equal to x and theta be equal to y. Don't use x and y. Treat them as x and y means they are playing the roles of x and y. That's what I meant by that. So let's see the solution. So the solution here, m is this theta square plus 1 times cos r and n is this 2 theta sin r. So in place of del m del y, because we are treating theta as y, so we now have del m del theta. So what will happen if you differentiate this partially with respect to theta? Cos r is considered constant, theta square will give you 2 theta and 1 of course does not contribute anything. So 2 theta cos r you are getting from this. From this means it is this. And then you also differentiate n partially with respect to r. In place of x now we have r. So if you do that, sin r will get turned into cos r and this time theta is considered constant. So you are getting the same thing. And this happens for all r comma theta belonging to the plane R2. And that's why you again write the usual things. So the given differential equation is exact in every rectangular domain D in the plane. Alright, and that is why such a function f will exist for which del f del r would be m and del f del theta would be n. That means these things. And then your usual method, you integrate this equation with respect to r. So theta is considered constant. So theta square plus 1 stays as it is. Cos r, when you integrate this with respect to r, it becomes sin r. You are not differentiating, okay? Don't put a minus sign. You are integrating. Plus phi of theta, where phi is a function of theta only. Now in place of y we have theta. And then of course from this second equation, where is it? Here. You get 2 theta sin r equal to del f del theta. But you calculate del f del theta from here. R is now considered constant. So you get 2 theta from this term times sin r plus phi prime of theta, the ordinary derivative of phi with respect to theta. So you can see that these two terms vanish means they cancel each other, and that way you are going to get phi prime of theta equal to 0. So from here you get phi prime of theta equal to 0, from which actually you get phi of theta equal to a constant, but because we want to take arbitrary constant here, so conveniently we take the value 0 and then use it back here. So that way we get this f, theta square plus 1 times sin r. So the general solution is f equal to, this time we use arbitrary constant c, that is theta square plus 1 times sin r equal to c, where c is an arbitrary constant. So that is the solution. And let me just end this video here itself. There are other exercises of course after this. It doesn't end here, that we will solve next week. So see you next week with more exercises and their solutions. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.